So the next speaker is Peter Keating. Early in his training in psychology in Dublin, Peter Keating became interested in how the brain learns to combine auditory and visual inputs. He then moved to the University of Oxford, where he did his master in neuroscience. And in his master project, he investigated how thalamocortical connection develop in the visual system. Then he joined Andrew King's auditory neuroscience group in Oxford, where he studied the development of spatial hearing and its maintenance in adulthood. He focused on how the brain adapts to asymmetric hearing loss with respect to spatial hearing. He is now a senior research associate in UCL, University College London, and by providing major insight into auditory processing, his work aims to make it possible to improve auditory function in specific environment or in hearing impaired population. So we will now discuss multiple adaptative process, maintain accurate sound localization following unilateral hearing loss.
Okay, thank you very much for that very kind introduction and for the invitation to speak here. So I'm going to talk about something really quite specific. So I'm going to talk about the effects of a hearing loss in one ear on sound localization. But the reason I'm going to do that is because I think it's a beautiful model system for, first of all, understanding some direct clinical implications of this, but also more generally to try to uncover some of the fundamental principles of how the brain works. And so as I go through the talk, I'm going to try to emphasize those things as we go along. Okay, so many different sensory impairments, they typically affect some sensory inputs, but they leave others intact. And so, for example, if you have hearing loss, then you can adapt to this by learning to ignore the auditory input and instead learning to rely more on the sensory inputs that remain intact. So, for example, vision and touch. But of course, many individuals with hearing loss will have some residual hearing still available to them. And in the world of cochlear implants, even individuals with profound hearing loss may have their hearing partially restored. And so this means that the brain can also adapt by learning to use these abnormal auditory inputs. But one of the difficulties with this is that in the case of both partial hearing loss and partially restored hearing, the level of hearing in each ear can be quite different. And this is a problem whenever you need your two ears to work together. And so the simplest example of this is if you have normal hearing in one ear and a partial hearing loss in the other. And inspired by the kinds of work on monocular deprivation that we just heard about, this has become a key model system for studying plasticity in the auditory system. But some of the biggest successes of this approach have come from looking at the effects of this on sound localization. And so sound localization is critical for many species, particularly when you need to locate things that you can't see. So for example, speakers who've hidden directly behind you. But it's also fundamental to communication in complex, noisy environments. And this is because spatial hearing helps you to segregate different sounds when there are multiple sounds at the same time. But unlike, say, the somatosensory or the visual system, where you effectively have an implicit map of space already at the level of the receptor surface, the auditory system has a map of frequency. And so this means that the auditory system has to actively construct these representations of auditory space from lots of different bits of information. And to do this, it uses a variety of different cues. So for example, if a sound is presented on one side of the head, it will be slightly louder in the ipsilateral ear, producing an interaural level difference, or ILD. But it will also arrive at that ear slightly earlier, creating an interaural time difference. And so these are known as binaural cues. But in addition to these binaural cues, the auditory system can also figure out where a sound is coming from just by looking at the input to a single ear. And that's because the head and ears filter sounds in a direction-dependent way. So for example, if you look at this plot up here, you can see that as the location of the sound has changed, the spectrum of the sound changes. And so if you know the spectrum of the sound, you can figure out where that sound came from. But of course, the challenge faced by the brain is to combine all of these different cues, so the interaural time differences, the interaural level differences, and the spectral cues, to create a coherent representation of space. And the challenge is even greater than that, because over time, each of these cues may change, not least because the size and shape of the head and ears may change during development. But because normal sound localization relies on these comparisons between the two ears, it's considerably impaired by a hearing loss in one ear. And this is because a unilateral hearing loss disrupts pretty much all of the spatial cues that are available to the auditory system, except for the spectral cues provided to the intact ear. And so the question that I'm interested in is, how does the auditory system adapt to this, particularly during development when the system is presumably at its most plastic? And so in principle, there's two ways that you could do this. So the first is that you could learn to use the abnormal cues by remapping these abnormal cue values onto the correct locations in space. And decades of research from Eric Knudson's group at Stanford has shown that this is precisely what barn owls do, both behaviorally and neurophysiologically. But for some reason, mammals don't seem to do this. And so this means that either mammals don't adapt or else they adapt in a different way. And so a second possibility is that mammals might instead learn to ignore the abnormal cues and instead rely more on the spectral cues provided to the intact ear. And so this is what we set out to test. And so to do this, we reared ferrets, so the exact type of ferrets that Shihab talked about earlier. So we reared ferrets with a hearing loss in one ear, and you can do this very easily by just inserting an earplug into one ear. But every now and then, we provided brief periods of normal hearing. So this meant that over time, these ferrets had a hearing loss in one ear approximately 80% of the time, and 20% of the time they had normal hearing. And so then later in life, we tested these animals on a basic sound localization task. And so in this task, ferrets stand at a little central platform, and then a sound is presented from one of 12 loudspeakers located around the periphery. And the ferret then approaches one of these loudspeakers, and if it's correct, then it gets a little reward. And if you test control animals on this task, then they do really quite well, so shown here in pink. And they score about 70% correct or so. But if you get these control animals to wear an earplug, their performance falls off a cliff, and they do really, really badly. But in comparison, if you look at juvenile plug ferrets, so ferrets that have been reared with an earplug, they do much better whilst they're wearing an earplug in one ear. So they've clearly adapted. But if you take the earplug out, so you give them normal hearing again, they do even better. And in fact, they're pretty much indistinguishable from controls. So the take-home message here is that juvenile plug ferrets adapt to an earplug, but they localize sounds even better when the earplug is removed. Okay, so to understand why this is the case, so we know they adapt, but is it because they're learning to rely more on the spectral cues provided to the intact ear? And we can address this by randomizing the spectrum of the sound across trials. And you can see an example of a random spectrum sound down here in black. And you see it's got all of these peaks and troughs in it. And we know from previous work that if you vary the sound spectrum across trials, then you make it very difficult for the auditory system to use monaural spectral cues. That's because it's very difficult to determine whether a particular spectral feature is caused by the filtering effects of the head and ears, or whether it's a property of the sound source itself. And so the prediction is that if our ferrets have adapted by learning to rely more on these intact spectral cues provided to the open ear, then as we increase the amount of randomization, then their performance, their percent correct, should decline. And if we test juvenile plug ferrets on this task whilst they're wearing an earplug, that's precisely what we find. But if we test the same animals again, but take the earplug out, so now they have normal hearing, we don't see this. And if we can just quantify this by calculating the slopes of these lines, and if you do that, you can see that here, and you can see the slopes are really quite different in each case. And so whilst the animals are wearing an earplug, the slopes are really negative, which is to say that randomization is hurting their performance. It's making it harder for them. But if you give them normal hearing, then the slopes are close to zero, which is to say that randomization is having very little effect on their sound localization performance. And so this means that juvenile plug ferrets learn to rely more on these monaural spectral cues, but only when wearing an earplug. So we can then ask, well, which particular spectral features are important for this kind of adaptation? And to address this, we can use a method based on reverse correlation. And this method works because if you look at the average of all of our random spectrum stimuli, and that's shown here in green, you can see that it's really pretty flat. But if you instead look at the average on trials where the animal responded to a particular location, and only that location, then distinct spectral features emerge. And so we can repeat this analysis for all of the different possible response locations. We've applied a threshold here just to get rid of some of the noise down here. And if we do that, we get something that looks like this. So these are all the possible response locations here, and this is frequency here. And I'm going to refer to this as a reverse correlation map. And so you can see that in these reverse correlation maps, in juvenile plug ferrets, you see these high frequency features emerge up here. But if we do the exact same thing for controls, we don't see this effect. And if we quantify this, we can show that the difference, so these features really only emerge at these high frequencies, so above 16 kilohertz. And so this means that these juvenile plug ferrets are adapting by learning to rely more on these high frequency spectral features. But we can now zoom in on this high-frequency portion of the reverse correlation map, and we can take away some of the thresholding. And if we do, that's what we see here. But if we now record acoustically the spectral cues that are provided to the intact ear, this is what they look like. And so hopefully you can appreciate that these two things look really remarkably similar. And so this is really strong evidence that these animals are indeed learning to adapt by relying on the cues that haven't changed, so the cues that are spectral cues provided to the intact ear. And you don't see the same thing if you look at the cues provided to the other ear. And if you compute these reverse correlation maps for controls, you don't really see very much of anything. And so all of this means that juvenile plug ferrets adapt by relying relatively more on the cues provided by the intact ear. But of course, what we really want to do is understand the neurophysiology underlying this form of adaptation. And so to do that, we're going to use virtual reality techniques to create virtual acoustic space stimuli. And that means that we can simulate both normal hearing conditions and a virtual earplug in one ear over earphones. And then we're going to perform bilateral extracellular recordings from primary auditory cortex in ferrets. And by using earphones, it means that we're able to manipulate the different cues independently. And so that means we can now ask, how sensitive are the neurons to different cues? And so based on the behavioral data that I just showed you, we have the really strong prediction that relative to controls, juvenile plugged animals should be more sensitive to the intact cues and less sensitive to the altered cues, but only in the presence of a virtual earplug. And this is precisely what we see, but to show this, we can just construct a weighting index. And so with this weighting index, higher values mean that the neurons care more about the spectral cues provided to the open ear, so these cues that haven't been changed by the hearing loss. And if we then compare that with controls, we can see that in juvenile plug ferrets, in the presence of a virtual earplug, the neurons care more about these spectral cues, shown here by higher values, than neurons recorded from controls. But if we then look at these again under normal hearing conditions, this difference goes away. And so this reweighting of spatial cues in primary auditory cortex is experience dependent and parallels that seen behaviorally. So to summarize this bit then, juvenile plugged ferrets adapt to an earplug by giving greater weight to the unchanged spatial cues provided to the intact ear. And from a clinical perspective, this is important because many hearing aids and cochlear implants have their microphones positioned just behind the ear. And since the high-frequency spectral cues that are important for this kind of adaptation are produced by the pinna, the filtering effects of the pinna, it means that these devices would not provide those cues. And so recently now with miniaturization, there's been a move towards moving these microphones inside the ear canal, initially I think for aesthetic reasons, but our work would suggest that there may also be functional benefits that patients could derive from having devices of this kind. So the second thing, though, is that primary auditory cortex shows experience-dependent reweighting, which parallels that observed behaviorally. And the third thing is that cue reweighting is not observed when normal hearing is available. And I think one of the really surprising aspects of the work I just showed you is that we can rear animals with a hearing loss in one ear for 80% of the time, and then when we restore normal hearing later in life, they're pretty much instantly, so as soon as we can test, they're able to use normal hearing inputs and they're able to localize sounds pretty much as well as controls. And this is directly relevant to glue ear. So glue ear is a condition that's experienced by approximately 80% of children before the age of 2, and it often produces a recurring hearing loss in one ear. And in some cases, surgery will be used to treat these children. And so I think knowing or having a better idea of exactly what the effects of recurring hearing loss are can better inform that cost-benefit analysis when it comes to doing surgery in what, in many cases, are very small children. So, but the wider implications of this are that plasticity of cue weighting can be specific to particular types of sensory experience. And so, for example, like lots of adaptation could happen in the brain, but if you don't expose the brain to the right sensory environment, you may not see any of that adaptation at all. And we know this from our own lives. If you have someone who's bilingual, so they can speak English and French fluently, if you never expose them, say, to a French-speaking environment, you may completely miss out on the fact that they are completely fluent in French. And so this is an important thing if you're going to look at plasticity in the brain. But more generally, the auditory system can learn and maintain different weighting strategies and switch between them depending on which sensory conditions are experienced. Okay, so all of that now tells us that ferrets can adapt to a hearing loss in one ear by using the second strategy, so they can learn to ignore the abnormal cues and instead rely on cues that remain unchanged. But I told you at the beginning that barn owls seem to use a very different strategy. And so the question then is, well, why do these different species seem to do such different things? And one possible explanation is that since birds and mammals evolved spatial hearing and sound localization largely independently, then perhaps they just evolved different adaptive mechanisms. But one of the interesting things of the data I just showed you is that ferrets adapted by learning to rely more on these high-frequency spectral cues. And since barn owls don't have hearing above about 10 kilohertz, they don't have access to these kind of high-frequency spectral cues. And so perhaps that's the reason for the difference. So we therefore wanted to know, well, what would happen if we took away these spectral cues from our ferrets? Would they still be able to adapt? Because if they can, then it suggests that they have access to a second adaptive mechanism. So to test this, we again reared ferrets with a hearing loss in one ear, so the exact same as before. And we again tested them on a sound localization task, again the exact same as before, except this time we used narrowband high-frequency stimuli. And we did this because if you want to use spectral cues, you have to be able to compare the energy at different frequencies. And so if you use narrowband stimuli, you prevent these comparisons from being made, which effectively makes spectral cues useless. And so if our animals can still do this task, then it suggests that there's some other form of adaptation going on. So if we test control animals under normal hearing conditions on this task, they do pretty well. And this is a joint distribution of stimulus and response. And so correct trials line up along this diagonal here. But if we just want to get an overall measure of performance, we can just calculate the average magnitude of the errors made by these animals. And if we do that, we can then normalize it so the score of 1 is chance and a score of 0 is perfect. And so we can see that control animals under normal hearing conditions, they're doing pretty well. So they score about 0.3. But if we get these control animals to wear an earplug in one ear, then they start to do really badly. And you can see an example of that up here. But in contrast, if you test juvenile plug ferrets that have been raised with an earplug, in the presence of an earplug, they do much better. And you can see an example of that here. So this suggests that juvenile plug ferrets possess a second adaptive mechanism that does not require spectral cues. So what exactly is this? And ideally, we'd like to know the answer at the level of the neurophysiology. And so again, we decided to perform bilateral extracellular recordings from the primary auditory cortex of ferrets. But we know from previous work that in ferrets, intraoral level differences are the primary cue for localizing high-frequency narrowband sounds. And so based on the behavioral data that I just showed you, we might expect to see changes in sensitivity to intraoral level differences. And so to test this, we can quantify spike rate, and we can plot that as a function of intraoral level difference. And we can do that for different sound intensities, so sounds that are different loudnesses. But if we just want to get an overall measure, we can collapse across all, so just average across all of these, and we get this thick line here, and then we can quantify the slope of this line. And so if this slope is really steep, it means the neurons are really sensitive to these intraoral level differences. And by convention, if they have a positive slope, it means that they preferred intraoral level differences that were louder in the right ear, so in our case, which was the open ear. And if you do this in control animals under normal hearing conditions, you see ILD slopes that are really pretty steep in both the left and the right hemispheres, but they're opposite in sign. And this isn't terribly surprising. And all it just tells you is that neurons in the left hemisphere tend to prefer intraoral level differences that are consistent with the right-hand side of space, and neurons in the right hemisphere tend to prefer intraoral level differences that are consistent with the left-hand side of space. But what's more surprising is if you introduce a virtual earplug to these animals, their ILD slopes, their intraoral level difference slopes go to 0, which is to say that they're not really sensitive to these intraoral level difference cues anymore. But in contrast, if we test juvenile plugged ferrets with a virtual earplug, they maintain sensitivity to these intraoral level differences. But interesting now, units in both the left and the right hemispheres prefer intraoral level differences that are louder in the open ear. And so this means that under plugged conditions, juvenile plugged ferrets show greater sensitivity to intraoral level differences than controls. And in juvenile plugged ferrets, neurons in both hemispheres tend to prefer intraoral level differences that are louder in the open ear. Now we can look at this in greater detail by looking at a much wider range of intraoral level differences. And if we do that, we can get ILD tuning functions that look like this. But the interesting thing about these functions is the peaks, and in particular the ILDs associated with them, which I'm going to refer to as best ILDs. And so we can see that in control animals under normal hearing conditions, these best ILDs line up on either side of 0. But if we then test juvenile plugged animals under the same acoustical conditions, we see that these best ILDs are shifted towards more positive intraoral level differences. And this is in the adaptive direction. So this is precisely what you would expect to see based on the barn owl literature. And of course, this just shows it for population averages, but we can do that for different neurons. And if we do, we can show that the best ILDs are shifted. So we see adaptive shifts in both the left and the right hemispheres in juvenile plug ferrets relative to controls. So this means adaptive shifts in ILD tuning are seen bilaterally in primary auditory cortex of juvenile plug ferrets. And this is a mechanism that resembles that observed in barn owls. So the next question we had then is, well, what can our data tell us about how sound location is represented by populations of neurons? And so one of the really successful models of sound localization in the literature is the two-channel model. And in the two-channel model, the location of a sound is represented by the difference in activity between two spatial channels. And in the model, the activity of a spatial channel is equivalent to the activity of a particular subpopulation of neurons. And so we can then ask, well, how do we define these two different subpopulations of neurons? And one way is we can define them on the basis of hemisphere. So perhaps sound location is represented simply by comparing the activity in the left and the right hemisphere. And this is known as the hemispheric decoder. But if we look at the neurons recorded from a single hemisphere, we can see there's a mixture of units with opposing preferences for interaural level difference, shown here by different colors. So that means within a single hemisphere, you'll find some neurons that prefer the opposite side of space, or at least interaural level differences that are consistent with the opposite side of space, and you'll find some neurons that prefer interaural level differences that are consistent with the ipsilateral or the same side of space. And so we could then define a decoder based on comparing the activity between neurons, subpopulations of neurons with opposing ILD preferences, which I'm going to refer to as the opponent process decoder. Now, with each of these decoders, we can then look at the population activity on a single trial, and we can then try to figure out, well, what was the stimulus on that trial? So what was the interaural level difference that was presented? And we can do that across lots and lots of trials, and we can again construct a joint distribution of stimulus and response. And this is conceptually identical to the behavioral data that I just showed you before. So again, as before, correct trials line up along this diagonal here. And again, as before, if we want to just get an overall measure of performance, we can just calculate the average magnitude of the errors made. And of course, we can do this for control animals under normal hearing conditions. And when we do that, we see that both the hemispheric and the opponent process decoder, they do a pretty good job. And if we quantify that, we can see that they score down here around 0.3 or so, 0.3, 0.4. But if we then apply these decoders to control animals with a virtual earplug in one ear, then the predictions of these decoders diverge to a greater extent. And if we then apply these decoders to juvenile plug ferrets raised with an earplug in the presence of a virtual earplug, the predictions diverge to an even greater extent. So the question then is, well, which of these decoders provides a better fit to our behavioral data? And if I show that here now in red, I think it's pretty clear that the opponent process decoder provides a better fit to our behavioral data. And so this suggests that intrahemispheric comparisons of activity are likely to be an important part of representing sound location. So it's not simply just representing the difference in activity between the two hemispheres. You may need to compare activity between neurons with different sensitivities to stimuli within a hemisphere. Okay, so to summarize this bit, juvenile plug ferrets can learn to locate sounds correctly using abnormal binaural cues. And so from a clinical perspective, this is important because it means that it's probably worth trying to restore hearing bilaterally, either with hearing aids or cochlear implants, even if you can't do a perfect job of matching the level of input to the two ears. But it also means that wherever possible, we should try to preserve these interaural level difference cues. And one of the problems with some hearing aids is that because the dynamic range compression is independent in the two ears, this can effectively mess up these interaural level difference cues. And so if you had a way of somehow preserving those to a better extent, then again, patients might benefit. And again, with the rise of miniaturization, there's now talk of hearing aids on either side of the head being able to communicate with one another. So we're now approaching an era where the technology might be there to preserve some of these interaural level difference cues. Okay, so also adaptive shifts in ILD tuning are seen bilaterally in primary auditory cortex of juvenile plug ferrets. And thirdly, an opponent process decoder provides a better fit to our behavioral data, which suggests that intrahemispheric comparisons of neural activity may be important for spatial hearing. And I think as Shihab mentioned earlier, there's a drive in the literature now to try to use EEG signals to try to control directional hearing aids. And the idea is that if you can figure out from the EEG signal where someone's attending, then you could make sure that those directional hearing aids, that they boost sounds that are selectively coming from that particular location. But But as we've just shown, that the hemispheric decoder fails if you have asymmetric hearing loss. And so this may constrain the kinds of decoders that you may be able to use in this case. Okay, but the wider implications of this are that abnormal hearing conditions may help constrain models of spatial hearing. And so from a scientific or experimental perspective, hearing loss and more generally sensory impairments, they actually provide an opportunity for really understanding fundamental things about the brain. And that's because you may have two models, and I just showed you, the impotent process and the hemispheric, where you can't really disentangle them using normal hearing conditions. But if you challenge the brain by exposing them to abnormal hearing conditions, then you may be able to distinguish which of them is more likely to be correct. But also complementary adaptive processes contribute to the developmental plasticity of spatial hearing. And importantly, this means that flexibility may help maintain accurate spatial hearing in diverse environments, and that different species may be more similar than was previously thought. But of course, this begs the question, what does this tell us about humans? So I've told you quite a lot about how ferrets adapt to hearing loss during development, but would humans adapt in the same way? And does the auditory system adapt in the same way in adulthood? So to address this, we then turned our attention to adult humans, and in particular undergraduates. And we know from previous work that if adult humans wear an earplug in one ear for prolonged periods of everyday life, so up to a week or so, then sound localization adapts using only one adaptive process. So people in adulthood, if they're exposed to hearing loss in one ear, they tend to just learn to rely more on the spectral cues provided to the intact ear. And this is, on the face of it, this is quite different to what I've just showed you in the ferrets. So we decided to ask, well, if we use a slightly different approach, can we maybe see something different? And so in particular, we asked our humans to come into the lab and only wear the earplugs in one ear when they're in the lab. And they came in for hourly sessions once every couple of days. And they did this for about 7 different sessions. And while they were in the lab, we then trained them on a sound localization task while they were wearing an earplug in one ear. And the questions that we had were, can adult humans adapt to this kind of episodic hearing loss in one ear? Does adaptation involve multiple adaptive mechanisms? And if so, how do these different forms of adaptation emerge over time? And so a lot of the methods we used were very similar, if not identical, to the ferret behavioral data that I've just shown you. So I'll gloss over those. Suffice to say that based on the behavioral data, we have 2 very strong predictions. And the first is that if our humans are reweighting, so by that what I mean is if they're learning to rely more on the spectral cues provided to the intact ear, then their performance should improve for flat spectrum sounds, but less so for random spectrum sounds. So this is exactly what I showed you with the ferrets. And so except now we can look at how this evolves over time. And so we can plot percent correct as a function of training sessions. And so we can see that for flat spectrum sounds, the percent correct increases quite dramatically over time. If we look at random spectrum sounds, we don't see this. And so this is consistent with this reweighting, and it suggests that these animals really are, not animals now we're talking about humans. These humans can adapt by learning to rely more on the intact spectral cues and are learning to rely less on the abnormal binaural cues. But if that's the only adaptive mechanism, then they shouldn't show any adaptation when we then take away these spectral cues. And so, again, the second clear prediction from the ferret data is that if subjects are remapping, so if they're learning to use the abnormal binaural cues, then subjects should still improve when we take away their spectral cues. And so again, we can plot the size of the errors made as a function of session, and we can see that the size of the errors made declines with training. And this is true not only at 8 kilohertz, which is where intraoral level differences are the primary cue to sound localization, but it's also true at 1 kilohertz, which is where intraoral time difference is the primary cue to sound localization. So this suggests that humans are able to adapt to this hearing loss in one ear by learning to use these abnormal binaural cues. So the next question we had then is, well, how does this adaptation emerge over time? And so we can now look at measures of remapping. So that's learning to rely more on the spectral cues provided to the intact ear, and reweighting, which is learning to use, or rather the opposite way around. So reweighting is learning to use the spectral cues to the intact ear. Remapping is learning to use the abnormal cues. And so we have these 2 different forms of adaptation. And so we can ask, how do these evolve over time? And so we can see that they evolve really with a similar time course. So they really seem to emerge together. So it doesn't seem to be the case that one happens first and then the other happens. They really do seem to emerge at the same time. And if we look at these measures of remapping and reweighting in individual subjects, so these dots now represent individual subjects, we can see that different individuals adapt in different ways. So we have one individual here who shows a lot of remapping and a lot of reweighting. We have some individuals that show a lot of remapping with very little reweighting, and we have some individuals that show a lot of reweighting with very little remapping. And one of the reasons for this, we think, is because these different forms of adaptation, they rely on frequency in different ways. So for example, if we look at measures of remapping at different frequencies, we can see that equal amounts of remapping happen at both high and low frequencies, which is to say that the amount of adaptation for interoral level differences is very similar to the amount of adaptation for interoral time differences. But if we look at frequency-dependent measures of reweighting, then we see something quite different. So we see a lot of reweighting at high frequencies and really not very much reweighting at all at low frequencies. And this isn't surprising in the sense that it's at these high frequencies where spectral cues are really most informative. And so this is perhaps then just caused by that. But it then inspired us to ask, well, do we say the same thing at a neural level? So on the face of it, this would suggest that perhaps different populations of neurons are involved in these different forms of adaptation. So to test this, we went back to our developmental ferret neurophysiology, and we can then look at measures of remapping and reweighting for different neurons. And if we do that, we can see that, again, we have some neurons that show a lot of remapping, but very little reweighting. And we have other neurons that show a lot of reweighting and very little remapping. But again, these differences, or this independence, is partially explained by the effect of frequency. So again, if we look at this adaptation, so measures of remapping in frequencies tuned to in neurons tuned to different frequencies, we see that it's pretty similar. So neurons that respond a lot to high frequencies, they show pretty much the same amount of adaptation as neurons that respond best to low frequencies. But that's not what we see for this other adaptive process. And in fact, what we see there is that neurons at high frequencies show a lot of adaptation, whereas neurons with low frequencies show very little. And again, this is consistent with the behavior. But I should point out, this is adult human behavior, and this is developmental ferret neurophysiology. So these are really quite different things, but nevertheless, some general features seem to emerge and be common to both. And so this suggests that remapping and reweighting emerge independently in individual subjects and neurons, which may be because each adaptive process depends on frequency in a different way. And so to summarize this, behavioral training enables adult humans to adapt to an episodic unilateral hearing loss using multiple adaptive mechanisms. And this is important from a clinical perspective because I showed you earlier that if you send, or rather previous work has shown that if you send individuals, so adult humans, out into the world with a hearing loss in one ear, so an earplug, for a week or so, they only adapt using one adaptive process. Whereas if we get them into the lab and we train them for just 7 hours, they can show both adaptive processes. So more generally, this suggests that some kind of behavioral training may help people to adapt to their hearing loss. But secondly, different adaptive mechanisms appear to be relatively independent of one another and may rely on partially distinct neural populations. But thirdly, individuals differ in how they adapt to hearing loss. And so again, from a clinical perspective, this is perhaps important to bear in mind. So for example, if someone will be unable to use a certain set of sensory inputs, then you may not bother trying to restore them. But on the other hand, if someone has these abnormal auditory inputs and is not finding it very easy to use them, then perhaps we could use some kind of training regime to try to help them to use them. And so the wider implications of this are that complementary adaptive processes contribute to the plasticity of spatial hearing throughout the lifespan and across different species, but also in addition to restoring auditory input, rehabilitation strategies might include training that helps people fully unlock the potential of whatever hearing they happen to already have available. And so to close, to finish, I'd just like to go back to something which I said again at the beginning, which is that if you have hearing loss, you can adapt to this by learning to rely more on the intact sensory inputs, so for example, vision and touch. But you can also adapt by learning to use the abnormal auditory inputs. But it turns out in the case of asymmetric hearing loss, you're faced with the same kind of choice. So you can adapt by learning to rely more on the sensory inputs provided by the intact ear, or you can learn to use the abnormal auditory inputs to help you localize sound. And so the take-home message from the work I've just shown you is that the brain doesn't actually have to make that choice. So the brain can use both of these different adaptive processes, and it can switch between them depending on what the sensory environment happens to be. And so this is not necessarily, there's no good reason why this should be unique to the auditory system. And so the same principles may work both within other sensory systems, but also across sensory systems. And so I think the wider implications of all of this are that when partial sensory impairments affect some sensory inputs more than others, then multiple adaptive processes may help the brain adapt. And this is helpful because sensory inputs don't just change as a function of sensory impairment, but they also change they can change quite dramatically across different environments. And so I'd just like to acknowledge some of the people who helped with this work. So Johannes Dahmen, who helped collect the electrophysiology data, Anayomi Rusino-Patton, who helped collect the human data, Andy King, who's been a great mentor and friend for many, many years, the Oxford Auditory Neuroscience Group, which is where I did pretty much all of this work, people who funded this work, people who fund me now, and of course I'd like to thank the organizers again for giving me the opportunity to talk to you today, and thank you for listening. And so, thank you very much.